Theorem 16 states that if x has a gamma distribution with parameters r and lambda, then the mean is equal to r over lambda, variance is equal to r over lambda square, and moment generating function is equal to the quantity of lambda over lambda minus t raised to the power of r for t is less than lambda. For the mean is equal to the integral of x function of x with parameters r and lambda dx evaluated from negative infinity to infinity. So let's substitute the value of the function, which is the integral of x times the quantity of lambda over gamma r times the quantity of lambda x raised to the power of r minus 1 times e to the negative lambda x dx, evaluated from 0 to infinity. So we combine like terms. We have the integral of lambda times lambda raised to r minus 1 over gamma r times x raised to r minus 1 plus 1 times e to the negative lambda x dx, evaluated from 0 to infinity. Now let's pull out the constant from the integral. We have lambda raised to the power of r over gamma r, integral x to the power of r times e raised to the negative lambda x dx, evaluated from 0 to infinity, is equal to lambda raised to the power of r over gamma r times the gamma quantity r plus 1 over lambda raised to the power of r plus 1. So we have gamma quantity r plus 1 over gamma r lambda is equal to r gamma r over gamma r lambda. So we cancel out gamma r, so our mean is equal to r over lambda. So for the variance is equal to the expectation of x squared minus the mean squared. Since we already got the value of the mean, which is r over lambda, we square it out, so it is equal to r squared over lambda squared. So in getting the expectation of x squared, we have the integral of x squared function of x with parameters r and lambda dx evaluated from negative infinity to positive infinity is equal to the integral of lambda raised to the power of r over gamma r times x raised to r plus 1 times e raised to negative lambda x dx evaluated from 0 to infinity. So we pull out the constant of the integral. We have lambda raised to the power of r over gamma r, integral of x to the power of r plus 1 times e to the power of negative lambda x dx evaluated from 0 to infinity. So we have lambda raised to the power of r over gamma r times gamma quantity r plus 2 over lambda raised to the power of r plus 2 is equal to the lambda raised to the power of r over gamma r times r plus 1 gamma quantity r plus 1 over lambda r plus 2. Okay, we simplify. So it is equal to r plus 1 quantity r gamma r over gamma r lambda square. We can cancel this one. So it is equal to r quantity r plus 1 over lambda square. And that is our value of our expectation of x squared. So by substituting the values of expectation of x squared and the mean squared, we have r quantity r plus 1 over lambda squared minus r squared over lambda squared is equal to r squared plus r minus r squared over lambda squared is equal to r over lambda squared. So for the moment generating function, it is equal to the expectation of e to the power of tx is equal to the integral of e to the tx f sub x of x with parameters r and lambda dx evaluated from negative infinity to infinity is equal to the integral of e to the tx quantity lambda over gamma r times lambda x raised to the power of r minus 1 times e raised to the power of negative lambda x dx evaluated from 0 to infinity. So combine all the common terms. We have the integral of lambda raised to the power of r over gamma r times x raised to the power of r minus 1 times e to the power of x t minus lambda dx evaluated from 0 to infinity. So we pull out the constant from the integral. We have lambda to the power of r over gamma r times the integral of x raised to the power of r minus 1 times e to the power of x times t minus lambda dx evaluated from 0 to infinity is equal to the lambda to the power of r over gamma r times gamma r over negative t minus lambda raised to the power of r. So it is equal to the negative lambda raised to the power of r over t minus lambda raised to the power of r. So we multiply it by negative 1 to get the negative. So we have lambda to the power of r over quantity lambda minus t raised to the power of r. So by law of exponents, we have the quantity of lambda over lambda minus t raised to the power of r, and thus the end of proof.